Hello and welcome to this acid and base review for Science 100. My name is Matthew Woods here at the College of St. Rose. I am the Assistant Director of the Academic Support Center, and I was asked by Mary Cosgrove to design this. All that you'll need for this presentation is found on the College of St. Rose website. There's a student packet that I ask for you to download, and you can fill it in as we go along. Now this is just going to be a basic review. I'm not going to get too much in depth and too much into the math and science. Just enough to get you what you need for your course. So let's talk about some basic properties of acids and bases. Acids taste sour and bases taste bitter. If you've ever eaten something with vinegar in it, vinegar is very sour tasting because it's made out of acid. Likewise, if you've ever tried antacids like Tums, they're flavored because they're made out of chalk, which is very, very bitter. Acids will burn your skin on contact. Bases will feel slippery to touch, like soap. And here's some big chemical things. Acids turn litmus paper red. Bases turn litmus paper blue. Acids turn phenolphthalein clear, and bases turn phenolphthalein pink. And phenolphthalein right here is probably the biggest acid-base indicator that we use in sciences here at St. Rose. So that's a term you're going to have to familiarize yourself with. Acids pH less than 7, bases more than 7. And here are just some examples. Vinegar is acetic acid. You've also got hydrochloric and sulfuric acids. Bases, ammonia, which is NH3. Soaps, and sodium hydroxide. Those are just some basic properties. And yes, you can tell I'm a child of the 90s. Let's get chemmy with it. I was a Will Smith fan a little bit growing up. There are two main definitions for acids and bases that we use in Science 100. These aren't the only definitions, but they're the ones that we're going to focus on. And the first one is the Arrhenius definition. Acids make hydronium ions in water, and bases make hydroxide ions. Anytime you see this IUM suffix on something, it tends to mean that it's positive. So this, hydro we know means water. This means positive. Acids make positive water. Likewise, IDE means negative. Hydro, of course, we know means water. So bases make negative water in solution. Now what does that look like? Well, here's HCl, which we know is an acid, plus H2O makes H3O plus and Cl minus. This is the positive water. This is hydronium. And here's a base, NH3, and this is hydroxide, negative water. All right, before we get into that. All right, so negative water, positive water. Hydronium, hydroxide. A little bit more chemy with it. Years went by, and we thought, that Arrhenius definition is nice, but it's not broad enough. We need to make it broader. So two chemists, Bronsted and Lowry, worked a lot with acids and bases and came up with a better definition. Acids will donate an H+, or a proton. Sometimes you'll see acids are proton donors, bases proton acceptors. H+, proton are the same thing. You need to remember that. So why is this better? If I go back to this slide, see how both of these have H2O in them? The only way that the Arrhenius definition works is if you have water. But HCl and NH3 can act as acid and base, respectively, outside of water. Let's go back to this one. So why is it better? We don't need the water. NH3 and HCl can interact with each other devoid of water and still act as acids and bases. Now, which is the acid and which is the base in this? Well, we know from experience that HCl typically is an acid, NH3 is typically a base. But what about over here? What's the acid, what's the base over here? Here's the way to think of it. Which of those look most like HCl? You should say Cl minus. What's the difference between these two? HCl lost an H, went to Cl minus. This is what's known as the conjugate base for HCl. So when HCl loses its H, acts as an acid, donates its H plus, and becomes Cl minus, this is now a base. All right, loses its H, becomes a base. Likewise, NH3 gains an H and becomes an acid. So it starts as a base, takes a proton. Over here, it's an acid, and we call these conjugates. So HCl and Cl minus are is a conjugate acid-base pair. HCl is the acid, Cl minus is the conjugate base. NH3 is a base, and NH4 plus is the conjugate acid. If at any time during this workshop you would need more assistance, my email address is on the College of St. Rose website and will be on the YouTube video description for you to use to ask me a question if needed. Just please put the name of the workshop in the subject heading. So you're going to practice this on your own. You're going to determine the acid-base pairs in each of these reactions. So, excuse me, I apologize if there was a loud burst of sound there. You're going to determine the acid, base, and the conjugate acid and base for both of these reactions. So please pause the video and solve it, unpause, and find your answer. For the first reaction, did you get this? H2O the acid, C2H3O2 minus the base. HC2H3O2 is the conjugate acid, OH minus is the conjugate base. For the second reaction, NH4 plus is the acid, H2O is the base, NH3 is the conjugate base, H3O plus is the conjugate acid. Now there should be something that you notice almost right away with these two reactions. That here water is an acid, here it's a base. Remember that water can act as either because its pH is neutral. And we're going to get into pH in a second. But because its pH is neutral, it depends on what you're adding to the water. If you add a base, it's going to act as an acid. If you add an acid, it will act as a base. Water is what we call amphoteric. A-M-P-H-O-T-E-R-I-C. Amphoteric. It can act as either or, and it depends on the situation. HCl will always be an acid. NH3 will always be a base. But water is a little bit different. All right, so I mentioned pH before. Let's talk a little bit about pH. What does pH measure? And this is something, and this stuff about pH is where there are a lot of common misconceptions about science and about chemistry. So let's try to correct those right now. pH does not measure strength. What it measures is the amount of H plus ions in solution, the concentration of H plus ions. And how it's calculated is the concentration of H plus ions equals 10 to the minus pH. So this is the power of 10. This is the concentration of H plus ions in molarity, moles per liter. And this is 10 to the minus pH. So something with a pH of 1 has an H plus concentration of 10 to the minus 1, or 0.1. pH does not ever measure strength of an acid. Never say that. If you say that, you are wrong in spreading misconceptions. In fact, let's emphasize that. pH does not ever measure strength of an acid. Strength of an acid has to do with how much it breaks up in water, how much it dissociates. HCl is a strong acid, not because it has a low pH, but because it completely dissociates in water. Acetic acid is a weak acid because it doesn't completely dissociate in water. Very little of it breaks up. So what is the H plus concentration in a solution of HCl that has a pH of 5? Well, you're just going to plug that in up here. 10 to the minus 5. So 0.00001 molar. And yes, that's a very low concentration. But what happens when the concentration to the concentration if the pH of the above solution is changed from 5 to 3? Are you more or less concentrated, and by what factor? So the first thing you've got to do is find what the new concentration is. So just like before, we're going to do 10 to the minus 3, and that gives us 0.001 molar. Now before we had 0.00001 molar, now it's 0.001 molar. Because there are fewer zeros in front of that 1, this is more concentrated. By what factor? So to do that, we take the final concentration, divide it by the initial concentration, and that tells us by how it increased. So it ended at 0.001, started at 0.00001, and so this divided by that gives me 100. So it's a 100-fold increase. What that means is it increased 100 times. Now you're going to try this one on your own. What is the H plus of concentration of a solution of acid that has a pH of 6? What happens if it goes from 6 to 9, more or less concentrated, and by what factor? Please pause the video, do the workout, and unpause for the answer. For the H plus concentration, did you get 0.000001 molar for the first part, 10 to the minus 6? For the second part, it's 10 to the minus 9, which is less concentrated than 10 to the minus 6, and it's a 1,000-fold decrease. Remember, it's still final over initial, even though this number is less than 1. Now let's relate what we just did back to the pH formula. When the pH went from 5 to 3, the concentration increased by a factor of 100. It got 100 times stronger. Stupid mouse. 100 is 10 times 10, so that's 10 squared. Well, 5 minus 3 is 2. So this is where we get this. The concentration of H plus we know is 10 to the minus pH. If we did 5 minus 3, you'd have 10 to the negative 2, which isn't the factor that it increased by. But if we did 3 minus 5, final minus initial, it's 10 to the negative 2, which is 10 to the 2, which is 100. I know that was a little confusing, but this is what we need to know. pH goes up, H plus concentration goes down. Every step up or down the pH scale is a multiple of 10. If I change by one step, either up or down, like 4 to 5 or 4 to 3, it's a factor of 10. If I go up 2, it's 10 times 10. If I go down 2, it's 10 times 10. We'll relate this to the pH and H plus formula by this. Delta H plus equals 10 to the minus delta pH. This triangle here, the Greek letter delta, means change. So the change in the H plus concentration equals 10 to the minus change in pH. And how we do change in science is final minus initial. So if the pH goes down from 5 to 3, let's say, like we just did, you'll have a negative number inside your parentheses times the negative number there to give you a positive. If it goes up from 6 to 9 like we did, you'll have a positive number here times a negative number to give you a total negative exponent. Remember, if at any time you need some assistance, please send me an email with the name of the workshop and the subject heading, and I'll be more than happy to assist you. Why do you need to know about acids? What's so important about them? What's the pH of rainwater and why? Now, rainwater is not naturally a pH of 7. Naturally, it's a pH of about 5.6. And why is that? Well, don't forget that in the air isn't just nitrogen and oxygen. There's a lot of carbon dioxide. And when carbon dioxide mixes with water, we make carbonic acid. That drops the pH. But what happens if it dips below this pH? What if it's below 5.6? That is, I'm sure you can guess by now, acid rain. How does that happen? How does it dip below that pH? There are a lot of reasons, but the one we're going to focus on in Science 100 is gases from burning fossil fuels react with water to make acids. What gases are involved and where do they come from? Carbon dioxide, CO2, comes from burning any fossil fuel. Coal, gasoline, natural gas, oil, any fossil fuel you burn will produce carbon dioxide. That's just a fact of life. NOx gases, NOx, either NO, NO2, NO3, come from exhaust in cars. Now, how does your car run? Your car runs on gasoline burning. Well, in order to burn something, you need to add oxygen to it. In order for your car to add oxygen, since you don't carry around a giant oxygen tank, is it sucks in air from the outside. Well, oxygen's not the most relevant gas in the air. The most prevalent gas is nitrogen. That nitrogen mixes with the oxygen in your engine, makes nitrogen monoxide and nitrogen dioxide, NO and O2, and that's let off in your exhaust pipe. Those mix with water and you get different nitric acids. Sulfur dioxide and trioxide, SO2, SO3, come from burning coal. Inside of coal there are pockets of sulfur. It's just how coal naturally forms. That sulfur, when you burn the coal, mixes with oxygen. You get SO2 and SO3, and that mixes with water to make different sulfur-based acids. All right, so carbon dioxide from fossil fuels, nitrogen oxides from exhaust in cars, and sulfur dioxide and trioxide from burning coal. All right, there isn't sulfur in other natural gases. Sulfur only comes from the coal. And what does acid rain do? Well, it damages ecosystems. Nutrients get leached from the soils. That means that things like sodium, potassium, magnesium, calcium, ions and nutrients that plants need to grow and animals need to grow end up forming mineral deposits, and we can't eat those. So nutrients are lost from the soil. Most organisms can't handle pH of rain, of anything really, below 5. So if their internal pH dips too low, they die. We can't really survive a pH below 7. So that tells you how specialized some organisms are. In lakes, there are aluminum ions in the water naturally. What the acid does is, just like the nutrients, causes them to come out of solution, and that causes a little bit of extra damage because that clogs the gills of aquatic animals. So now they can't breathe. Acid rain will decay some bedrock. Limestone gets decayed by acid rain. And what that does is that it'll eventually just eat away at buildings and things like that because it's going to erode them. Acid rain will decay iron, will decay steel, it'll eat away marble, it'll eat away limestone. All these things react with the acid and then just get washed away in the water. This is a pretty famous side-by-side picture. This is a statue of George Washington. It was built probably in the 1800s somewhere. And here it is 100 years later. Notice how much damage that statue has undergone. That's all due to acid rain. No other real weathering has occurred. So that's just the damage acids can do in the rain. What about bases? What's the pH of normal water? And now, yes, you can say it, the pH of normal water is in fact 7. What happens when the pH is raised above that? Well, that usually means you have hard water. That's water that has highly charged metal ions like calcium and magnesium dissolved. And that causes damage to pipes and soap scum. It can lead to pipes bursting and things like that. But is hard water bad for you if you drink it? Actually, not really. In fact, some doctors say that that's a good supplement for calcium and magnesium if you don't get enough of them in your diet. So that's all we have to do for acids and bases. Again, if you have a question, feel free to email me at my email address provided in the video description. Otherwise, I hope you enjoyed and have a good day.